Great. Um, okay, good morning, everybody. Um, so, yeah, if you need problem solving for today, I have them, and your previous problem solvings are on the table. So, today we will talk about random forest, but before that, I want to correct myself. So last time we introduced the notion of impurity as the fraction, uh, the number of points in left node over total number of points times the quality factor. Here for left node, and the same for the right node. And this was our quality factor. And for regression, we had the entropy, or this measure of uncertainty. For regression, we used MSE. So it was 1 over total number of points in the parent node and sum over all values y. And I said that we don't need to use this factor 1 over number of points, but was my mistake, because if we use this factor, then this formula will look as follows. And by the way, I compared the result with scikit-learn, and in scikit-learn they use this formula, where by impurity they mean MSE with division by n. But if we multiply by the number of points in left and right node, actually this division by n will cancel out. And we will get sum of squared residuals for quality factor. So, as you remember, I said to use sum of squared residuals instead of h, but the sum of squared residuals actually will be in the quality factor. So this is the correction from last time. So we take, for example, the average over left node. Actually, here I should write for I such that our point belongs to left node. And this term also we will use MSE instead of SSR. So these factors will cancel out, and we will get the sum of, oh, wait a second, here should be squared residuals, I'm sorry. It should be y minus y bar. And here it should be y minus prediction in the left leaf. And here it should be y minus prediction in the right leaf. Okay, so these factors will cancel out, and we will get the common factor 1 over number of points and sum of squared residuals in left and right node. So I remembered sum of squared residuals, but this was quality factor, not the h. So the final formula will be 1 over v, the number of points, sum of squared residuals in left node plus sum of squared residuals in the right node. And because this is the number of points in the parent node, it's just a factor, and we actually will minimize the sum of squared residuals in both left and right lists. So last time I also said that if we minimize this quality factor, the prediction will be the average. So let's prove that. So let's start with proving this. So if we want to minimize this sum, I will rewrite it. You don't need to do this, but it's just important to understand. So, and now I'm not using the factor 1 over b. So we want to minimize this with respect to unknown parameters are predictions in our lists, yr and yl. So we just take a derivative. And when we take the derivative of this quality factor, partial with, for example, yl, we will get this sum, but without square. Well, and also -1, but it's not really important because we will equate this to 0. So the first term will be the sum of y points, and the second term, because it's a constant, it will be just the number of points in the left node. The number of points in the left node times prediction. Well, and from this formula, we can solve it for y. L. It will be 1 over number of points in the left node times this sum. Okay, so we proved that if we minimize this quality factor, the prediction in the node will be the average. So what if we minimize MAE? So instead of sum of squared residuals, we will take just the sum of absolute errors. So it's a little bit more tricky because absolute value is not differentiable. We can take the derivative, but we can use our intuition. I don't want to prove because it will take maybe 1 or maybe 1.5 pages to prove that in case of MAE loss, so if our quality factor, impurity is the sum of absolute errors, sum for I from 1 to the number of points of absolute errors, then the optimal value of the prediction in the node will be median. So let's just look at some examples, and I hope it will be, at least you will get the intuition. So let's say we have points 5, 6, and 10. And I want to place point y here, such that the sum of distances from these points to my new point is the smallest one. So does it make sense to choose the point outside of our range? And no, because then we should calculate the distance to every point, and of course it will be greater than if we place this point inside our range. But what is the best choice? What is the best choice? To place our prediction such that the differences between y and 5, between y and 6, between y and 10 is the smallest one. Hmm? I think you should know that. So, okay, I will give you a hint. What if it's different from the central point, from 6? For example, if it coincides with point 6, then we will have zero difference for 6, a unit difference for 5, and 4 units for 10. So in total, it will be 5. What if we place this point somewhere here? Then we will have the distance from this point to 5 plus this point to 6, 1. But distance from this point to 10 will be greater than 4. So what is the best choice for y star? The middle point. Yes, and it's called median. So in this case, y star is the median. But what if we have, for example, extra point, 4 points? What will be now the best choice for y star? Yes?
I'll say 5, that's like it's between like 0 and 10.
5 works, but another one?
Anywhere between 5 and 6.
Correct. Any point in between these two, because if we choose y star as 5, the distance to 6 will be 1. If we choose y star as 6, the distance to 5 will be 1. And for any, and if we choose point in between, the distances to 5 and 6 also will sum up to 1. So you remember from school that median is the average between, in case of the even number of points, the average of the intermediate points. But actually, it's any value in between. Will minimize our. Okay, that's it from last time. Now we are going to model ensembles, and Matt will help us with the first method, which is called voting. So I will open the presentation. One sec. Decision trees. Okay. Yeah. The correct. I think you don't know answers to the
I won't take it with me this time either.
I think you don't know the answers for the questions. And if you want to write there is a marker. I mean,
Okay,
one
to
count.
vote. Yeah, sounds good. Yeah,
I did not get the machine learning problems in.
Yeah.
there you go.
But first we'll have a little bit clear before we go into problem solving.
All right, so the idea here is that voting, just like you vote in real life, you have multiple models to decide what your end result is going to be. So here we have a couple of kind of like what we went over last time, decision trees that have various parameters. So this one up here, max depth of 3 and mid samples is 15. So you can see that's a pretty even split. And then as we change those parameters to allow more, I guess, overfitting, you can see here where we have no max depth, so we can have as many splits as we want, and min samples to be 1. So that means that the smallest number of items and individual data points that are encapsulated within a split is just 1. So you can have just complete overfitting. We have quite a bit of different models that result from that. And so what we can do in order to figure out how to classify one point based on all of these models is we do voting. So it's like an aggregate of all of the predictions from each of these models to decide what our classification is going to be. And I think this should be that combination. So this is the result, right? So you would sum up, for example, let's take this triangle point. So you would look at how it's classified in each of these models. That's a bad example because in every model it's classified as 1, but maybe this, we'll take this square here. So here it's classified as 0. Over here it's classified as 1. Over there it's classified as 1. And in every model, it's classified as 1. So what would our result be in our aggregate? Does anyone know? If it's classified as 0 and 1, yeah, 1. So if we look here, we have this square, and it's classified as 0. So you go through and do that with every point, and that's how we get this decision boundary. Any questions on that? So then we can do this kind of voting just with ourselves in like a little game. So the first question is it what campus was image 1? All right, what campus was image 1 taken at? Any guesses? I'm gonna write these down and then we'll vote.
Give choices.
Do you have choices? Okay. Well, we'll list the campuses,
One is
right?
Croatia, another is
Dubai.
Yeah.
Kosovo, right? We'll stick with that, I guess. Croatia, Dubai, and Kosovo.
No, we have just 2 here.
Oh,
Croatia
whoops.
and Dubai.
All right.
Yeah,
Never mind.
let's ask students what is for the first image.
So yeah, this first image, image 1, raise your hand if you think it's Croatia. Okay, 1, 2, 3, 4.
I think you don't need to count.
All right. All right, so it looks like Croatia wins. And that actually is Croatia. Anyone want to say how they knew? Go ahead.
Because like the second picture is obvious giveaway that's like Dubai because of like the settings because I've been there.
Oh, cool. Okay, good guess. Anything else? Yeah. Yeah, that's how I figured it out when when I was here. What about image 2? Any guesses? Yeah.
What's the first sign?
So what was your guess? For image 2. Okay, cool. Yeah, so that is Dubai. So that's kind of like voting.
This method is called
Voting. Oh.
Majority.
Okay.
Majority vote. So we classify images based on like the maximum models classification.
Yep, and then we can do that with a couple other things. So does anyone know what country this is from?
This
This
is actually the symbol.
Yeah.
I'm like 90% sure it's like Belgium.
Belgium, okay. That's one of our guesses. Anything else? Yeah. Netherlands? Any other guesses? All right, so we're between Belgium and Netherlands. Raise your hand if you think it's Belgium. Okay, pretty even.
6.
Yeah. What about for Netherlands?
1.
Just one? All right.
2.
So it is Belgium, right? So that's
Yes.
correct.
Yeah, it's those many countries.
Mhm. And then what country do we think this was taken in? Yeah,
This is obviously the Eiffel Tower in Las Vegas.
right. So we have US. Any other guesses? Really? Yeah.
I think I heard that the Eiffel Tower was actually in France.
In France? All right, that's a good guess. Any other countries? All right, who thinks US? All right, we have 2. Who thinks France? All right, great. It is in France. Good guess.
And it was actually multi-class classification because we have actually it's another next question. How many?
Okay. Is this Brussels or Paris? Raise your hand if you think it's Brussels. Yeah, you think it's Brussels?
Yeah, I'm just guessing.
Okay. What about Paris? Any guesses for Paris? Quite a few. Anyone want to share why they think it's Paris? Yeah?
Like the car tax, like even though they're blurred out.
Okay. I don't remember which one this is.
It was Paris.
It is Paris. Oh, look at that. Great work. And then we can also do this with regression, so not just classification. So how many countries are in the world? I'll write down a couple of guesses and we'll take the average. So raise your hand if you want to shout out a guess. Yep. 192. Anybody else? Yep.
261.
261. Anyone else? Let's get a couple more than two guesses. Yeah. 185, you said? 195. Any other guesses? Yep. 223. Yep.
198.
198. Anyone who has a calculator handy want to take the average of that?
Yeah,
I can do it as
go
well.
to Wikipedia and find the answer.
Yeah, all right, I'll do that while somebody averages it out. Is anybody calculating the average? Should I do it? All right, thank you. I think that's the number, right?
There will be a table of all the countries and that's the last number. There are also some territories which are
Mm.
the
195, it looks like. Yep. So we're a little off, but not too bad for guessing. So, if we were our individual models and we each guess that, it's not terribly far away considering the magnitude. So not bad.
Yeah, but what if we take median? And
That's a good question. Yeah. So let's
what is
see.
the median?
We have our lowest is 192, 261, 195, 198. So it's even worse.
Yeah,
223.
yeah, okay.
Yeah, so you're a little bit skewed. But yeah, not too bad.
Control tab.
Okay. Yeah.
I think like the median is like 198. It's like
Did I do it wrong?
it's like
Oh, I did.
it should be
192, 261. Oh, you're right. This would be crossed out, so it'd be 198.
Yeah,
Whoops.
then
Thank you for pointing that out.
then it looks closer.
Yeah, that is a little bit closer. Cool. And then what's the lecturer's age? I think this is you, not me, right? It's a little bit easier for me. Any guesses? I'll write some down. We'll do the same thing. Anyone want to guess?
It won't- it don't-
That's a little
great.
Yeah.
I guess 43.
43.
Yep.
Whoops. Any other guesses? Yep.
52.
52. Mm-hmm.
35.
35.
Oh,
yeah.
Any other guesses? Yep.
55?
55. Yep.
59?
59. Anyone else? Yep. 49.
In one class, we have 90 samples.
Anyone else? Yeah.
Outliers.
62.
62. Damn.
Yeah, it's good to have outliers.
Any last guesses? Okay, great. I'll average them up, I guess. I don't have to look
Yeah, you
this
don't
up.
need to calculate it. Maybe somebody will tell you. Or you won't.
Maybe somebody will beat me to it. All right, I got 50.7, so rounding 51. Yep.
Okay, what about median?
Median, let's see. I'll try and do it right this time. 35, 62.
Because you remember when we have outliers, the MAE is more stable for the MSC.
40, then it would be 49 and 55. So 52 would be our median. So a little bit higher.
Yeah, okay. The right answer is 43. I don't want to pay them to do that.
No, that was a good guess. Did you know that?
No.
Oh, wow.
It's also completely random.
Oh, wow. All right. Good guess. Is this the diagram we just looked at?
That's it now. Yeah, so that's it about what.
Yep.
All right, continue with voting on subsets. Thank you, Ned.
Yeah, thank you.
At least I hope you get idea now how we can aggregate multiple models, like multiple experts. Oh, thank you. Even
Me for the rest, or?
well, do you want? I think I will do the problem solving.
Sounds good. All right.
Because I found this mistake about Formula 4.
Yeah, I had that in my
SSR.
notes from last semester too, so that's good to know.
Okay, you could see that even without any knowledge, the aggregation of the answers resulted in pretty accurate result. So, yeah, the other option is to use one model instead of using multiple models, to use one model, but train this model on different subsets of data. Like take a half of data and train this model, then take another half and train this model. So we kind of will get different predictions. And this is another idea to use, in this case, I used 90%, I believe, for every picture, 90% of data. But because they were chosen randomly, we have different decision boundaries. And if we aggregate now these predictions, the result looks pretty smooth. So, like every individual model was overfitted. We had like this long lines, blue regions, and the aggregated model. Here I just used majority voting because it's classification. Looks pretty good. So the next idea, which is used in statistics, is called bootstrap. In bootstrap, instead of using samples without repetition, we will use samples with repetition. So, for example, here we have points index 1, 2, 3, 4, and I can sample them with repetition. So some points can repeat. I will have exactly the same number of points, 4, but the indices can repeat now. Like here, 1, 1, 2, 3, or here, 2, 3, 4, 4. So again, we will have different subsets for the models, but as in the previous case, we used smaller subset. In this case, we will use the same size subset, but with repetitions. And why it's called bootstrap? because if you want to estimate, for example, in statistics, the average, like 1 over n sum of points x I will use now lowercase, then this is just one number, mean. But in statistics, we're interested in confidence interval, like what are the lower and upper boundary for mean. And from one sample, we can't get this estimation. If we had several samples, like then we could calculate one average. For another sample, we can calculate another average, and then we could calculate the variance of these means, and this is how we get this confidence interval. But what if we have just one set of data? So we don't have several sets of samples. In this case, we can apply this bootstrap idea and create, for example, another subset of data. Now, I don't know, I can maybe denote this X with index B bootstrap. It means that some X's can repeat. Then I can again apply bootstrap or sample with repetitions, and I can get several numbers m, and then it will allow me to calculate the variance and confidence interval for estimator for mean, even with one sample set. Does it make sense? So, and we will use the same idea in our model aggregations. We will train models on different subsets obtained by Bootstrap. So one comment, the number of unique elements in this Bootstrap samples is about 63%. How can we get this number? So if we calculate opposite event that would actually that we didn't choose a point, it will be 1 minus 1 over total number of points. And the probability that we didn't choose this point on step 1, on step 2, on step 3, and so on, will be just this probability power n. And do you remember from calculus what is the limit of this expression? Actually, if I add here minus, so I should add here minus and power -1. So what is the limit of this expression? Yeah. Yes, Euler's constant exponent. So it will approach to 1 over e, which is 2.7. And if you calculate this, it will be about 30-something%. And 1 minus this number will give you 63%. So this is how you can estimate. So if you have a pretty large data set, then you this number will represent pretty accurately the number of unique points in the Bootstrap subsample, and about 30% points will repeat. Okay, now we're ready to do the problem solving. Okay. Because the first problem is about Bootstrap aggregation. Okay, so you're given this data. Now we have two-dimensional data. By the way, I didn't mention we will have midterm, and I will give midterm over break and 2 days after break. So you can do this after break or during break. And there will be a question also with two-dimensional features. So now we'll actually will understand how to work with two-dimensional features. Yeah, and also I have forgotten to give probability questions in homework 5. I also will add these questions to the midterm because it will be take home. So 2 extra questions. Short. Okay, so I worked as the random number generator and generated 2 bootstrap subsets. So you can see x1 repeats twice, x2 repeats twice in the first sample, and here x4 repeats 3 times. So the task is to build the decision stem for both bootstraps, and then use these 2 models. In other words, just aggregate them to get the tree. Okay, and first step is to write sorted data for feature 1 and for feature 2. So I will create 2 tables, x1y and x2y. As you remember, we should go through all possible thresholds and choose the best model, but because we have 2 features, we also should do this for both features and choose also the best feature. Because in our node, we make a decision only by 1 feature. So let's sort by x1, 1, 2, 3, 3, 5, 5, 6, 7, 5, 5. Oh, wait a second. My bad. First, we should take the bootstrap. So I'm sorry. So first, I will take the bootstrap x1, x2, y, and after that, I will actually build table x1 and y. So for the first bootstrap, we repeat the first point twice. So it will be the first line from our table twice. Then twice second line. Then 3 points with index 3. Then 6. 1, 2, 3, 4, 5, 6. 5, 4, 3, 7, and 8. And I can do also bootstrap samples for the second bootstrap. So x2 x3, x4 3 times. X5, 6 and 7. Okay. Now we can sort. Let's do the first sample first. We have 1, 1. So I sort by x1, 2, 3, 3, 5 twice, and 7. And I can also sort by the second coordinate just to get table ready. Ew. Um, Where's my phone? Oh, my phone is a good thing. Okay, so okay. 3, 4, and 5. Actually, just looking at these two tables, you can maybe immediately guess which feature is better, x1 or x2. What do you think? Which feature is better? So you can notice that for the same x, we have very different y's. So even without calculations, you can say, okay, we can just work with the first feature, but let's do calculations. So, and our splits, do you think, what do you think? Okay, let's just calculate this splits. Actually, there are 4. So for the first split, and let's see. Oh, I'm using the old version in, let's open the new version. Yeah, I actually did these calculations to show that our quality factor will be very easy to calculate. It will be just the sum of errors. Okay, so for the first split, I recommend to use the left half of your page for the first bootstrap and right for the second. So now we're working with the first bootstrap. For example, for the first split, quality factor I will write maybe just once the full expression, and then we will use this simplified expression. It will be 1 over, oh, sorry, I should write actually the split, x1 greater than 1. What will be the predictions in left and right nodes if we use MS mean average error? So for the left node it will be 1, and for the right node we should take the median. What is the median here? So we have 1, 2, 3, 4, 5, 6 points. So the median will be any number, but we will use the average, for example, between 2 and 3. So it will be 2.5. So these are predictions 1 and 2.5. The total number of points 8. The number of points in the first node 2. And then we use quality factor, but with 1 over number of points. They will cancel out. And what is the sum of these pairs? 1 minus 1 plus 1 minus 1. For the second, it will be, what is it? It should be 2.5. 2.5. Well, 2 also works. So times 0. And here we have 4 points over 8. 1 over 4 times the sum of errors here. So, oh, it will be large. So 1 minus 2.5 absolute value will be 1.5. I won't remember. I should write 1.5. Then the difference with 2, 0.5. The difference with 3 also 0.5. And the difference with 6 3.5. And so in future I will just cancel out these factors, and because it's much easier just to sum up the errors. Okay, so let's look at the second split. So on your paper you can just write below. I will write here. Second split for x greater than 2, x1 greater than 2. And predictions in the left 1, prediction in the right will be, now the median will be 3. And quality factor, we will have 0 for the left node. And what will be the sum of errors for the right node? 2 minus 3, 2 minus 3, 3 minus 3 will 0. So 2 minus 3 is 1, plus 1. And 6 minus 3 is 3. So 5. Then the next threshold, x1 greater than 3. the predictions will be it will be again 1 for the, because it's median for the left node, and 3 for the right node. So the quality factor, we just sum up the errors. We will have error for 2. It will be error for the left node. And we have error 6 minus 3 for the second node. Okay, so you can see that these splits are resulted in the same quality factor. And the last split, x greater than, oh, let's see, that's 5. x1 greater than 5. The prediction in the right node is 6. In the left, the median will be 2. And the quality factor for this split, so we have errors with 1, 2, 3. And we have errors with 3, 1, 2. Oh, again, 5. Okay, if you look at the second tree, and let's look at the, so we can split here between 1 and 6, so we can split only here. If you look at, or here, if you look at the threshold x2 greater than 1 or x2 greater than 2, I promise you will get higher values for quotes. So the prediction here will be 1, and the median here will be 1, 2, 1, 2, 2, 2. Here the median will be 1, and here median will be 2.5. But if you look just at one error between 1 and 6, you get 5. But you will get also errors with prediction 2 and 3. So the value will be greater than 5 for sure. And the same for the 7th split. I don't know. You can just try that it will be greater than 5. So we will choose the first feature, but which actually 3 to choose. We have 3 with the same quality factor. I don't know, it's just arbitrary. I would use maybe one like in between, just because it's kind of splits in equal parts. But in cold, it will just maybe flip a coin which one to choose. So let's use second split, for example. Because it doesn't matter which one, I will use the second split. Now let's, so we built the decision stamp for the first bootstrap. Now we should do the same for the second bootstrap. And let's first sort our points by x1 and x2. And again, you will figure out immediately which feature is better. And we won't even calculate it. And the main sign is that for the same feature, we have different targets. So this is the main sign that it's not a good actually feature to choose. So 1, 1, 1, 2, 6, and 3, 4, no, 3, 2, 3, 4, 4, 3. So I hope you can see immediately that this feature is not good because it's kind of mixing the targets, and we will have a large error in any split. So let's look at the first one. And where should I choose the splits? What do you think? Here or here? Greater than 2 or greater than 3? It looks like a pretty nice split because we have the same value for almost all points. Okay, let's just calculate. So, for the first split, I should write the decision tree x1. Okay, so we decided that the first feature is better immediately. X1 greater than 2. The prediction is 1, and median here will be 2. The error with for the first node will be 0. The error for these points will be 0. For 3 will be 1. For 2 will be 2. And for 6 will be 4. We compare with prediction 2. Now let's look at the second split, x1 greater than 3. The prediction for left node will be 2. And prediction for this will be 4. So quality factor. We have just one error in the left node, 1. And we have difference 2 with, let's see, no, difference 1 with 3. And we have difference 2 with 6. And you can see that quality factor second is smaller. So this is our choice. Now we have 2 decision trees, and we can aggregate. So now we can calculate y-pred. Let's see. 0.12. the first model will predict y because 1 is smaller than 2. The second model will predict 2. So the prediction here will be 1.5 because we take the average between these two predictions. Actually, I can write the prediction of one model and the second model. Just to make it more clear. Second point 3, the prediction of the first model will be 3. The prediction of the second will be 2 because 3 is not greater than 3. So the prediction will be 2.5. Then 2 is greater than 1, so the prediction here, sorry, it's not greater than 2, 1. And 2 is smaller than 3, so 2. The prediction will be 1.5. 3, we have this prediction for 3, it's 2.5. 6, this model predicts 3, this model predicts 4. So we will return, the aggregation will return 3.5. 5. Well, 5, 7, and 5, so it will be the same because we will get the same predictions for x greater than 3. Great. Now, let's talk about random forest. Can I erase my writing? So, what if if instead of going through all possible features in the node of our decision tree, we will just choose a subset of features. Just, for example, randomly choose, if we have, for example, 100 features, we randomly choose 10 features and we'll choose the best feature, but not between 100, but between these 10 features. Then we will get a random tree. So random tree is the decision tree, but when on every step, we choose only from the small number of features instead of going through thresholds for all possible features. And when we do this bootstrap aggregation of random trees, it's called random forest. So, okay. I think I have definition, random forest. No. So random forest is the bootstrap aggregation. So we use a random subset of data, but also we, when we make a decision in every node, we make this decision only for limited number of features. So why this model actually works? Let's talk about bias variance decomposition. For every model, the error has 3 components: bias, variance, and error. The noise, we can control, so we can't control our data. The bias, what do you think for linear regression, if I want to approximate this function? does the bias large or small? Is the bias large or small? For example, on the next image, I plot the decision tree of the or where bias is smaller for decision tree or for the linear function, if I want to approximate sinusoid, or the just guess. Yes.
It's I mean like for this case it's usually on arch. The bias.
For which?
Well, I mean like for bias it's going
For linear or function or for decision tree?
for point of view. I mean like go the next image. Yeah, yeah, for this one. This is gonna be arch.
But doesn't it look like closer to the sinusoidal function than the previous one?
Okay.
So
I mean like the previous one was like that's right, but like the one that we should up to the right, that's relatively large. That's more large than this small one.
well, but if you look at the data, then you will get pretty high deviations from this line. So linear regression has the highest bias if we compare with nonlinear functions. So to reduce bias, you can just choose a model with smaller bias. That's why people choose decision trees. The variance you also can control because the formula for the sum of for the variance of the sum, as you remember, it's kind of if we have sum over n, then it will go outside of this variance as 1 over n squared. And the sum of n numbers will result in n times variance. So 1n will cancel out, and finally we'll get 1 over n times variance. But also we have covariance. So if we wouldn't have covariance, then with increase of number of models, we will decrease the variance. So the idea is to use less correlated models. That's why we build models on subsets of data, or we choose just some subsets of features, because in this case, our models will be less dependent. And here's illustration how the correlation depends on the number of features that we use for the split in every node. If we use just small number of features, the correlation is low. But when we increase the number of features which we take in consideration for split in every node, then the correlation increases. So that's why it's better to use in the random forest trees, and there is actually a recommendation how many features you should use for splits. For example, for regression, it's 1/3 of features. For classification, it's square root of the number of features. And this was proposed in the paper that actually Breman proposed decision trees, and also he proposed random forest later in 80s, decision trees and later random forest. So here is the result. If we build these different random trees and aggregate them, then we will get not maybe very precise, but pretty accurate estimation of our function. We have some peaks here, but you can increase the number of trees and you will get better prediction. So we have 1 minute left and we don't have time for the last question. So we will just skip the last question. In the last question, I asked you to use feature 1 for the first bootstrap and feature 2 for the second bootstrap, kind of in decision truth in random forest when we in random truths we choose one feature randomly, not by the best split but randomly. But okay, we will just create one program. Don't forget to write your name on it, and tomorrow I will publish the midterm program. So we can do this all break or later.
This is say RR, right?
Oh, it is free. It should be,
And then for the first step, it should it be 2 eighths, 1/2, or 6 eighths, 1/6. 0, 4 eighths, 1/4, right? And 3 6 eighths because we have
oh, you're right.
and the 6 is cancel out, and then that's why you have the 1/8, 1/8. and
You're
that.
right. Oh, you also go so pretty or both models predict three and 4. So it will be 3.5. Yeah. Yeah, because that's one is greater than 3, 5, 7, 5. So prediction will be great. So one model predicts 3, another model predicts 4. And yeah, 3.5 for the next. Yeah, because 3 is not greater than. Oh, I use another stream. Sorry, I use because they
And then it's like fine. Yeah.
the multi-factor I use this one. But if you use this one, then it would be wow. Yes, but I use this. Actually, I erased, but yeah, yeah. It kind of randomness. Welcome.
Sorry.
I have a question.
Yes, Ryan. Yes, and
Are we allowed to change the cost matrix in this function?
why?
It's like for class 4, it's not fine if it's based on like when I change
Oh.
change the cost matrix, like it's fine if it's class.
So let's because it show you how your code for plus for cost. And this is oh, maybe you just need to transpose it. Yeah. Yeah, that's fine. If you just transpose them, I think it's
But like it doesn't box for it.
okay. It should again.
It's like flash 3. I think.
Well. I believe there.
Yeah.
I believe there should be a piece of this code in my video recording because
Yes, that's way more complicated.